So here we have question number 46. Two disks are rotating about the respective axis of rotation with angular speeds 2 radian per second and 5 radian per second are brought into contact such that their axis of rotation coincide. Now, the angular speed of the system becomes 4 radian per second. If the moment of inertia of the second disk is 1 times 10 to the negative 3 kilogram meter squared, then the moment of inertia of the first disk is so. So this is a clear case of conservation of angular momentum. So you have one disk that is rotating, actually two disks that are rotating, and their angular speeds are 2 and 5. So we will take the total initial angular momentum, set it equal to the total final angular momentum. Angular momentum is the product of rotational inertia and angular velocity. So I1 omega 1 plus I2 omega 2 is equal to I1 plus I2 times omega. So where I1 and I2 are the moment of inertias of the two disks, and then later on, because they are brought together, they're brought into contact, so they become one object. That is why the total moment of inertia is now I1 plus I2. So from this, for the second one, we know the I is 1 times 10 to the negative 3 times 5. For the first one, we do not know I1. That's what we're trying to find. Omega 1 is 2. And then when you add both, you would get I1 plus 10 to the negative 3. Okay? So times omega is 4. So now solve this to find I1. So that first term is 2I1. And then 5 times 10 to the negative 3. There, when you distribute these two, you get 4I1 plus 4 times 10 to the negative 3. And then, okay, let me speed that up. So collect the I1 terms together. So you have 2I1, because 4I1 minus 2I1 would be 2I1. And then 5 minus 4 is 1, so that's 10 to the negative 3. You see, 5 minus 4, 1. And then you divide, you would get 0.5 times 10 to the negative 3 kilogram meter squared as the answer. 47. A wheel is rotating at 1800 rotations per minute about its own axis. When the power is switched off, it comes to rest in 2 minutes. Then the angular retardation in radian per second squared, it should be radian per second squared, is, so we have the initial RPM. Rotations per minute will not work. We have to change it into rotations per second. That will give us the frequency. Once you have the frequency multiplied with 2 pi, you will get the angular velocity, because angular velocity is 2 pi times frequency. So that is the answer, and we're going to get it like this. The initial angular velocity is 2 pi times 1800 divided by 60, because the 60 seconds in 1 minute. So that is the frequency, see? That is 60 pi. Then final angular velocity is, of course, 0, because it comes to rest. Time taken is 2 minutes, which is 120 seconds. And alpha can be calculated using this formula, omega f minus omega I by t. So omega f is 0, omega I is 60 pi divided by 120, and that will give us negative pi by 2 radian per second. But the question asks us for angular retardation. So what we got is angular acceleration. If the acceleration is negative, that means the retardation is pi by 2 without the negative. Okay, so the retardation is pi by 2 radians per second squared. 48. If the angular momentum of a particle of mass m, so that's a particle, mass m, rotating along a circular path of radius r with a uniform speed is L, so the angular momentum is L, mass is m, it's a particle moving in a circular path of radius r, then the centripetal force acting on the particle is. So we have to find the centripetal force. Centripetal force is mass times velocity squared by radius. We'll start from there. So, and angular momentum is I times omega. Okay, I times omega. What's I? I is the moment of inertia. But for a particle, the moment of inertia is mr squared. And omega is v by r, linear velocity by radius. So that simplifies to mass times velocity times radius. Okay, so we can rearrange that to get L is equal to, V is equal to L by mr. You see that? We made velocity the subject. Now we can find the centripetal force. The centripetal force is mass times velocity squared by radius. And we are going to substitute for velocity. But there is a square, so we have to square all the terms. So that's why I've squared all of these three terms, because it's velocity squared. Now simplify, you will see r and r squared combining to become r cubed in the denominator, and the mass gets mass and mass squared will leave you with a mass in the denominator. So you get that. So that is the centripetal force, L squared by mr cube. 49. Pick out the wrong statement from the following. The SI unit of universal gravitational constant is Newton meter squared kilogram raised to minus 2. Okay, that is correct. The gravitational force is a conservative force. That is correct. What is the conservative force? Where the work done does not depend on the path taken. So you lift an object, you can go from this point to this point, you can go straight up, or you can go along this path. The work done will be the same. That is why gravitational force is conservative. So that is correct. The force of attraction due to a hollow spherical shell of uniform density on a point mass inside it is 0. That is correct. Inside a hollow spherical shell, there is no gravitational force, so it is 0. D. The centripetal acceleration of the satellite is equal to acceleration due to gravity. That is also correct. That's why every satellite is actually falling with the same acceleration as the acceleration due to gravity. But why doesn't it reach the surface of the earth? Because it's falling at the same rate as the earth is curving from under it. See, the curvatures are the same. So that means the answer is gravitational potential energy. E, that is a wrong statement. Let me show you why it's wrong. Because gravitational potential energy is actually the product, okay? Or gravitational potential, you will see how I write it, and you see the difference. Gravitational potential is gravitational potential energy divided by mass. See the difference? So that is almost like a trick. So gravitational potential is potential energy divided by mass of the body or mass of the object. 50. If a body of mass m has to be taken from the surface of the earth to a height h is equal to r, then the amount of energy required is. So you have an object on the surface of the earth, and from there you have to take it to a height, and the height must be equal to the radius of the earth, okay? So what is the work done? Or what is the energy required? That is the question. Diagram should make it easier. That is the answer. But we'll start with potential energy at the surface is given by this formula, minus gmm by r. So that's a formula for potential energy. So notice there is no square there. That's a mistake that students make. So potential energy is gravitational constant multiplied by the product of the masses divided by the radius, with a negative, of course. So when you take this object to the height, now the gravitational potential is going to become minus gmm by r plus h. But h is the same as r, so it will become r plus r, which gives you minus gmm by 2r. Are you with me? Because the question says that it is taken to height h is equal to r. So now the total distance from the center of the earth is r plus r, 2r. Okay? So now we can find the change. Let's find the change in the potential energy. The change in potential energy would be the difference between the two. So change in potential energy is minus gmm by 2r minus, so final minus initial. That is the final and that is the initial. So take the difference. When you look at it carefully, you see that one is half, the other is full. So it's like minus half plus 1. And also notice there are two negatives there. So it becomes a positive. So it's minus half plus 1. What is minus half plus 1? That's plus half, right? So that's why you have half gmm by r. So that is actually the work done, but we don't have any of those answers like that. So we got to substitute by using the idea that when the object is on the surface of the earth, gmm by r squared is equal to mg. Because the gravitational force can be written in two ways. It's either gmm by r squared or mg. So from there, we can cancel out the mass and you get gm is equal to r squared g, which we can substitute now here in place of gm. We will substitute as what? R squared g. So r squared gm by 2r, and that will give us mgr by 2. That's how we get the answer to that question. Okay? 51. The total energy of an artificial satellite of mass m revolving in a circular orbit around the Earth with a speed v. So now we're looking for the total energy of this satellite. Basically, a satellite has potential energy and kinetic energy. But when the satellite is so far away from the Earth, we assume that it's at infinite distance, so the potential energy is zero. Remember, the potential energy decreases as the distance increases. Correct? So potential energy is zero, so that means the only energy that it has is kinetic energy. So that's why the answer is 1/2 mv squared. That is easy, because that's the formula for kinetic energy. 1/2 mass times velocity squared. But the concept is that when r becomes infinity, EP, potential energy, becomes zero. And therefore, the only energy that the satellite has is kinetic energy. And I'm bringing some math there and trying to show it to you. 1/2 mv squared, but velocity is root gm by r, so the total energy I'm going to prove is negative gmm by r, see that, plus 1/2 gmm by r. So now if you look at this, it's minus 1 plus half. See, minus 1 plus half, that gives minus 1/2 gmm by r. But what is that? When you substitute like we did before, that is 1/2 mv squared. That makes sense? So that's why it's a negative 1/2 mv squared, but energy cannot be negative, so it's like, okay, that's 1/2 mass times velocity squared. 52. Oh, it's a good one. Two soap bubbles, each with radius r1 and r2, coalesce, means combine, in vacuum under isothermal conditions. So temperature is constant. So two soap bubbles become one. So if the radii are like 3 and 4 centimeters, like 3 centimeter and 4 centimeter, we're going to show that the radius of the bigger one is not 7 centimeters. That's one of the choices. That's wrong. It's actually 5 centimeters, which is you take the square root of the sum of their squares. Okay, I'm going to prove it. For proving this, we will use Boyle's law. Why? Because Boyle's law is applied under the condition that temperature is constant. So here it's an isothermal process, which means temperature is constant. So we're going to apply Boyle's law. What is Boyle's law? Pressure times volume is a constant. You heard me. Pressure times volume is a constant. What is the pressure? Now, inside a soap bubble, because of surface tension, there is an excess pressure. And the excess pressure is 2T. Actually, it's a bubble, so it'll be 4T by R. Okay, excess pressure inside a soap bubble because of surface tension is 4T, where T is surface tension. 4T by R1 is the first one. So for the second one, the excess pressure is 4T by R2. And the volume of a sphere, bubble is a sphere, is 4 by 3 pi R cube. So 4 by 3 pi R1 cube for the first one. 4 by 3 pi R2 cube for the second one. Now that we have the pressure and the volume, you can take the product of the two. So initially, P1V1 plus P2V2 should be equal to P times the final volume, right? Okay, so P1, we're going to substitute for P1 as 4T by R1. V1 is this whole thing, 4 by 3 pi R1 cube. And then same thing for P2, 4T by R2. And volume 2 is 4 by 3 pi R2 cube. And then, it moves on so slowly. Okay, is equal to the pressure, excess pressure for the big bubble is 4T by caps R. I'm using capital R as the radius of the single final bubble. Okay, so cross out everything we can. So 4 by 3 pi cancels out on both sides. 4 by 3 pi, all of that. 4T cancels out. And then you have R1 cube by R1. What is that? That is R1 squared. Same thing here. So R1 squared plus R2 squared is R squared. So that means R should be square root of R1 squared plus R2 squared, right? R1 squared plus R2 squared. So that's a combination of surface tension and Boyle's law. So 53, the ratio of hydraulic stress to the corresponding strain is known as. So when you hear the word hydraulic, that means it's connected to fluids, liquids or gases. Hydraulic. What is the modulus that fluids have? Fluids don't have Young's modulus and rigidity modulus. Fluids only have bulk modulus. The word bulk is related to volume. Fluids undergo change in volume, right? You can't twist a fluid. You can't change the length of a fluid. So that's why bulk modulus is the answer, because bulk modulus is defined as you will see, let me, force by area. So normal force by area divided by change in volume to the original volume. So F by A, that's called the hydraulic stress. And then change in volume by original volume is called the volume strain, okay? So hydraulic stress by volume strain gives you bulk modulus. Just want to say compressibility is the reciprocal of bulk modulus. Young's modulus, that's only for solids, is linear stress by linear strain. Expansion coefficient, well, that's to do with an entirely different topic. It's to do with expansion of anything when it's heated, okay? 54. A boy can reduce the pressure in his lungs to 750 millimeter of mercury. Okay, so when he just pulls the air and using a straw, he can drink water from a glass up to the maximum depth of atmospheric pressure 760 millimeter of mercury. So we have to, if this boy can reduce the pressure in his lungs to 750 centimeter of mercury, 750 millimeter of mercury, then how big can the straw be? So from a glass up to a maximum depth of, this is simply the formula for pressure. What is the formula for pressure exerted by a liquid? H rho G. Okay? And on the left side, it's the change in pressure. So atmospheric pressure is 760 millimeter. This boy can reduce it to 750 millimeters. So the change in pressure is 10 millimeters of mercury, right? So we should be able to find that easily. Let's go. So the change in pressure is equal to H rho G. The change in pressure is 75 times 13.6 times. Oh, wait. That's not right. The change in pressure is 1 times. What is that 1? Where did I get that 1 from? 1 times 13.6. I'm doing it in centimeters. I can see that. So see, this is 76 centimeters and this is 75 centimeters. 76 and 75, the difference is 1 centimeter. And then that's because the density is given in gram per centimeter cube. So that's the density. 980 centimeter per second squared is the value of acceleration due to gravity. I know you're used to 9.8, but in centimeters is 980. So that's the excess pressure is equal to, now on the right side, what is he drinking? He's drinking water. So on the right side, we're trying to find the height. We will use the density of water, which is 1 gram per centimeter cube times 980. The 980s cancel out and you get H is equal to 13.6 centimeters. So that's the maximum depth from which he can drink that water using the straw. Oh, here I'm trying to show how I got the 1 centimeter, but I'm sure you got it by now. 55. A spring stores 1 joule of energy for a compression of 1 millimeter. Oh, if you compress the spring, you're doing work. So you make it store energy. The additional work to be done to compress it further by 1 millimeter. Oh, here the catch is the additional work to be done. So what we'll do is, we know that when you compress it by 1 millimeter, the energy stored is how much? Is 1 joule. So now you're again compressing it by 1 millimeter. So that means the total compression is 2 millimeters. And the work done or the energy stored is not 2 joules. I'm going to show you that it's 4 joules. Because the formula for energy is 1/2 K x squared. You see the square there? So when 1 becomes 2, it's actually doubling. But because of the square, it becomes 4 times. Let me show that to you. Okay, so the energy of a spring, it's actually potential energy of a spring, is 1/2 kx squared or k delta x squared, whatever way you want to write it. So in the first case, 1 joule is equal to 1/2 K. We don't even need K. K is the spring constant. We don't even need that. We don't know that. 1 squared. And I'm like leaving it in millimeters because it's a ratio. It's going to cancel out. And then x joules is equal to 1/2 K 2 squared. You see, I'm going to show that x is surely 4 joules. You can see that from there. And therefore, the additional energy, is 4 minus 1, 3 joules. So the answer is 3 joules. You got to be careful about such problems with catch words like this. Additional work done. 4 joules minus 1 joule, that is 3 joules. All right, so 56. If m represents the mass of each molecule of a gas and T its absolute temperature, then the root mean square velocity of the gaseous molecule is proportional to root mean square velocity. What is the formula? Square root of 3RT by m. That's one of the formulas. That's what we need here. So the RMS velocity is square root 3RT by the mass. And then T half raised to m raised to negative half is so clear because square root of something means T raised to half and mass is in the denominator, so it's m raised to minus half. That's why this is the answer. That's easy. 57. A Carnot engine operating between temperatures T1 and T2 has efficiency 0.2. In a Carnot engine, you have the source and the sink. The source is at temperature T1, the sink is at temperature T2, the efficiency is 0.2. When T is reduced by 50 Kelvin, its efficiency increases to 0.4. Its efficiency increases to 0.4. Then T1 and T2 are respectively. Okay, what is T1 and T2? T1 and T2 are respectively what? We got to find that. It's distracted a little bit. Sorry for that. So you have two sets of equations now. Okay, efficiency. Formula for efficiency is E is equal to 1 minus T2 by T1. 1 minus T2 by T1. And so first it's given that the efficiency is 0.2. So you get that equation. So that's our first equation. And then the efficiency becomes 0.4. But this time T2 is reduced by 50. So it became T2 minus 50. Is that making sense? So that is T2 minus 50 because the temperature of the sink was reduced by 50 Kelvin. So I want to rearrange this and put it as T1 minus T2 by T1. Let me write this and then I'll show you an easier method. It's the same thing. Let me finish this. This one, again, when you distribute, it's minus T2 plus 50 by T1. Okay. That is actually T1 minus T2 by T1. I'm going to split that plus 50 by T1. And then we know that this whole thing is 0.2. Isn't it? Yeah. Because T1 minus T2 by T1 is 0.2. So I know this whole thing is 0.2. Then I see that's what I'm writing now. 0.4 is equal to 0.2 plus 50 by T1. And I can solve for T1. So a little bit of math there. Take this 0.2 to the other side. 0.4 minus 0.2 is 0.2. 50 by T1. So T1 is 50 by 0.2, which is 500 by 2. So it's 250 Kelvin. Okay, so if you get T1 as 250 Kelvin, then of course you can calculate T2 from one of the equations. I'm using the first one. So I'm writing it in green so you don't get confused, okay? So solve that. You see that 1 minus 0.2 becomes 0.8. And then T2 is 0.8 times T1. So you get 200 Kelvin. So 58, a molecule of a gas has 6 degrees of freedom. Then the molar specific heat of the gas at constant volume. So you have to know 6 degrees of freedom. What kind of a molecule is this? If it has 6 degrees of freedom, that means it has 3 degrees of vibrational freedom along the X, the Y, and the Z. 3 degrees of vibrational freedom and 3 degrees of rotational freedom. See, it can rotate about the Y-axis. It can rotate about the X-axis. See that? And it can also rotate about the Z-axis. Okay. That means it is a polyatomic molecule. That means it has either got 3 or more molecules. Something like carbon dioxide, nitrogen dioxide, because you have to know 6 degrees of freedom is for a polyatomic molecule. Okay, so that means we should know that the ratio of specific heats of this gas is 1.33. 1.33. Okay, let me write it down so you see that. So if we know that, we can calculate the specific heat at constant volume because it's given by this formula. R by gamma minus 1. This is the universal gas constant. This is the ratio of specific heats. Okay? So R, we know, the answers are in terms of R, so we need not do anything there. So gamma, like I explained, because it's a polyatomic molecule, gamma is 1.33. Okay, so how do we know that? Because it has 6 degrees of freedom. We know it's a polyatomic molecule, and therefore gamma is 1.33. If it was diatomic, it would be 1.4. If it is monoatomic, then it would be 1.67. So we have to know that. Now, coming back, 1.33 can be written as 4 by 3. So this is 4 by 3 minus 1. When you do the math, you get 4 minus 3 by 3, which is 1 by 3. And that means that 3 will go to the top. So you get 3R as the answer. Okay, so that's how you work it out. But like I said, if it is a monoatomic gas, you have to know, because next time they may ask you about that. So gamma is 1.67. If it's diatomic, then gamma is 1.4. All right. So those are the constants that you kind of have to know. All right. 59. The total number of degrees of freedom of a rigid diatomic molecule. Oh, we just spoke about that. If it's diatomic, then it has 3 degrees of vibrational freedom because it can vibrate along the X, along the Y, you see, along the Y, and it can vibrate along the Z. But when it comes to rotation, it only has 2 degrees of freedom because the rotation about the bond axis, because it's diatomic, there are 2 atoms, that is negligible. Why? Because the moment of inertia will be small. So that's negligible. So you only have 5. 3 vibrational plus 2 rotational. So that's a straightforward idea that you had to have. So a diatomic molecule has 3 vibrational plus 2 rotational, totally 5 degrees of freedom. So what about a monoatomic molecule? Can you guess? It only has 3 vibrational. Single atom, it can move along the X, the Y, Z. Nothing about rotation there because it's negligible, all 3. All right, so 60. If the differential equation for a simple harmonic motion is d squared y by dt squared plus 2y is equal to 0, what is the time period? So we have to know the general differential equation for simple harmonic motion. What is it? It's d squared y by dt squared, let me show you, plus kx is equal to 0. That is the general form. So d squared y by dt squared plus, I'll write ky because we're talking about y here. So plus ky is equal to k by my is equal to 0. So the general form, the general differential equation for simple harmonic motion is d squared y by dt squared plus k by my is equal to 0. You know that k by m is actually omega squared. Okay, anyway. So that means k by m is 2 in this case because they gave it as 2y. So, and then the formula for time period is 2 pi root m by k. So if k by m is 2, then m by k is 1 by 2, isn't it? Okay. So 2 pi square root 1 by 2 is nothing but pi root 2. Because this 2 can be written as root 2 times root 2, and one of the root 2's will get cancelled, and the other root 2 will remain here. So that will be root 2 times pi, which is the same as pi times root 2. Okay, so you got that. 61. Identify the wrong statement from the following. If the length of a spring is half, the time period of each part becomes 1 by root 2 times the original. Yes, it's correct. The unit of spring constant, I'm jumping, this one is Newton per meter. That's right. The spring constant is inversely proportional to the spring length. Yeah, because if it's a short spring, then the spring constant will be bigger. It's tougher to stretch it or to compress it. The time period of a stiffer spring is less than that of a soft spring. Yes, because a stiffer spring has a bigger spring constant, and time period would be, in that case, it would be small. So the answer is B, because the effective spring constant of a spring in parallel is actually K1 plus K2. This is the formula when springs are connected in series. So they just reversed it, see? So remember, when two springs are connected in series, that's when you use 1 by K is 1 by K1 plus 1 by K2. So the other one is for parallel. All right, 62, the total energy of the particle executing simple harmonic motion of amplitude A is 100 joules. At a distance of 0.707 A from the mean position, what is its kinetic energy? So you're given the total energy, and then you're asked to find the kinetic energy. So we have to know the formula for total energy. The formula for total energy is 1/2, okay, let it come by. Total energy, it's 1/2 K A squared, okay? 1/2 times K A squared. And that is given as 100 joules. So we're going to say 1/2 K A squared is equal to 100. So from there, we can find what K is making. Or first, let's write what KE is. What is the formula for KE? KE is 1/2 K A squared minus X squared. A squared minus X squared. So that's the formula for KE. Now, X is given as 0.707 A. See that? X is the distance from the mean position, or displacement rather. That's given as, okay, so X is given as 0.707 Okay, so I'm going to substitute it there. I actually distributed this, so there are two terms. And why did I get 0.5? Because when you square this number, 0.707, you get approximately 0.5. So that's why I got 0.5 A squared when I square it. So now you see that you have half here, and you have half times 0.5, which is 1 by 4. So half minus 1 by 4, okay? What is half minus 1 by 4? Half minus 1 by 4 is 1 by 4. Okay, you could do it that way or like I did. So either way, you would get half Ka squared, again 0.5, that is 1 by 4 Ka squared. Okay, all right, so let me see what I'm writing. So I put it that way, and then we know 1/2 Ka squared is 100, right? So instead of this, I put 100, and so 100 times 0.5 is 50. So either way, that's the answer, 50 joules.